Hello everyone, welcome back to CSP channel, Learn Easy Way of Physics. This is Chary, Physics faculty. We have to go to discuss about stationary waves or standing waves. Stationary waves or standing waves. Here is both waves, either longitudinal waves or transverse waves, having same amplitude with the same frequency, traveling along the straight path with the same speed, but they are moving in opposite directions. They are superimpositions. Okay, like that, a new set of waves are called as stationary waves. Here, when string is attached to two rigid supports, when it is getting vibrations, the stationary waves are formed. After their combination, superimpositions, this type of new set of waves are called as stationary waves. Here is one wave is traveling in the forward direction, another wave is traveling in the opposite direction of that first one, and nodes are formed here and antinodes are formed here. In the stationary waves, nodes and antinodes are formed. Nodes, where the vibrations of the particles, vibrations of particles are minimum called nodes. They are nodes where the vibrations of the particles are minimum at their positions are called nodes. Here is the vibrations of the particles are minimum at these places. So already the nodes are indicated in the diagram, and antinodes, where the particles or where the vibrations of the particles, or maximum called antinodes. So here is the vibrations of the particles are maximum, means the amplitude is maximum at this place, okay, the amplitude is maximum at these places, the amplitude is minimum at these places. So here is antinodes where the vibrations of the particles are maximum. Okay, they are called antinodes. Here is the distance between two successive nodes is lambda by 2. Distance between two successive nodes, or two successive antinodes. Okay, that which is equal to, here is lambda by 2. Distance between two nodes or two antinodes, that is lambda by 2. Here is distance between node and antinode is lambda by 4. Distance between node and antinode Antinode which is equals to, here is lambda by 4. The distance between node and antinode is lambda by 4. Okay, the distance between two successive nodes or two successive antinodes is lambda by 2. The distance between node and antinode is lambda by 4. Don't forget these points. They are the very, very important. Write these points. Okay, we have to take the displacement of the first wave. Let the displacement of the first wave is y1, that is equals to where the wave is traveling, it is moving in the forward direction. Hence, the displacement of the wave equation is y1 equal to a sine of kx minus omega t. Okay, now the second wave is traveling in the backward direction, and its displacement is y2 a sine of kx plus omega t. So both displacement of the wave equations here, and we have to find out the resultant displacement. So according to principle of superposition. We know that the principle of superposition, and we discussed in the previous class, that is the resultant wave displacement which is equal to sum of individual displacements. Now I am writing here y is equal to y1 plus y2. So we know that y1 and y2, these two equations can substitute in the place of y1 and y2. A sine of kx minus omega t plus and a sine of kx plus omega t. It is in the form of sine a minus b, and it is in the form of sine a plus b. We can express it according to sine a minus b. We know that that is sine a cos b minus cos a sine b. Like that we have to express, and that is equals to a sine kx cos omega t minus a cos kx sine omega t. Now plus sine a plus b, a sine kx cos omega t plus a cos kx sine omega t. Now already expressed according to the sine a minus b and sine a plus b. Here is minus a cos kx sine omega t and plus a cos kx sine omega t. So they are cancelled. And the resultant displacement equation is y is equals to 2a. Here is a sine kx cos omega t. Here plus a sine cos omega t. A sine kx cos omega t. Okay, both will add it. And 2a sine kx cos omega t. Here 2a sine kx is resultant amplitude. This is resultant amplitude, and it depends on kx. So if x is equal to 0, comma lambda by 2, comma 2 lambda by 2, comma 3 lambda by 2, so on like this. So at the positions, the vibrations of the particles are minimum. Those positions are called nodes. Here is nodes. You can represent nodes. So if x is equals to, the position will take x is equals to, here is lambda by 4, comma 3 lambda by 4, comma 5 lambda by 4, so on, so on, so on, like this. We can take like this, no? So here is the vibrations of the particles are maximum. They are called antinodes. So antinodes. So at that positions, the vibrations of the particles are maximum. We know that where the vibrations of the particles are maximum at antinodes. So at antinodes, the vibrations of the particles are maximum. Here is write these points. And here is the standing waves. Standing waves on a string. On a string. Fixed at one end. At one end. And here is taking one of the rigid support like this. Okay. Here is one of the string is taken and it is attached to the rigid support. Okay, when it is plugged, get its vibrating of the string, it can be formed a number of stationary waves here, and at the last end of the wave is taken. Here is open end of the wave, and the direction of the waves are indicated like this. It is in the forward direction. And the next one is the direction of the wave is in opposite direction, like this. It is coming to backward direction. But here is, it is attached to the one support, one end of the rigid support. So here is taking, these are nodes, we know, and these are antinodes. Here is the length is taken, that is lambda by 4. Now we discussed. The distance between nodes and the antinode is lambda by 4. And here is, let us consider one mode which is open end of the open end of the wave. So I am taking here like this. At the last end of the open end of the wave is taken here like this form. Okay, this is antinode, the direction is like this and like this. And here is the node, the distance between node and antinode is lambda by 4. Okay, now its total length is L. So P is equals to 1. The first mode, complete, not complete mode, this is open end of the wave. Here is taking, what is the length of this open end of the wave? Here length L is equals to taken as lambda by 4. Considered lambda 1, first wavelength, and here is we have to calculate the wavelength, that is lambda 1. Lambda 1 is equals to, here is 4L. Now the wave velocity or speed of the wave, I can write it here, V is equals to under root of T by mu. We know that T is the tension in the string and mu is the linear density of the string. Linear density, and here is V. The velocity of sound after vibrating of the string, its velocity V is equals to N1 lambda 1. We have written like this. And we can substitute V. Here V is actually T by mu. That is equals to N1 into, what is lambda 1? Lambda 1 is here 4L. We need to calculate N1 is equals to, let us consider N, that is equals to, here is 1 by 4L into root T by mu. This is the fundamental frequency of the vibrating string. Okay, it is N1 equal to N equal to 1 by 4L and the root of T by mu. So first harmonic this is, and the second harmonic at one end I am taking here. This is wait, and like this. This is first one, and the second one is opened like this. Okay, its length is L, and the direction of the wave is like this, and lambda by 2 here, from here to here, lambda by 2, and this is antinode, and this is antinode. Here distance between node and node, that is lambda by 2. Here distance between node and antinode, that is lambda by 4. Finally, what we can write it here, that length L is equals to, here is lambda by 2 plus lambda by 4. That is equals to here 4 and 2 lambda plus lambda. Finally, that is equals to 3 lambda by 4. This is L. Okay, 3 lambda 2, we considered lambda 2. Then we have to calculate lambda 2 value. Then lambda 2 is equals to, here is 4L by 3. Okay, same as follows. Here is V is equal to, we know that, under root of T by mu. And the next one is the velocity of sound, V is equals to, here is N2 lambda 2. And V under root of T by mu, we know that is equals to N2 into, what is lambda 2? Lambda 2 is here 4L by 3. 4L by 3. Then we can calculate the second frequency. This is second harmonic, no? So harmonic means like multiple vibrations of the waves. Here is N2 equal to, we can write it 3 by 4L under root T by mu. So we should take common 3 here, 1 by 4L under root T by mu. Under root T by mu. Now that is equals to, N2 is equals to 3N. N2 equal to 3N. So that is the second frequency equal to 3N. If two harmonics are formed like that also, and next one is third harmonic. We are taking the third harmonic. Two complete modes are formed and another end is open end of the wave. Like this, here is, I am writing 1, 2, and the next one is, here is like this. Okay, here is antinodes. It is coming to backward direction. Antinodes. Antinodes. Here is also antinodes. Nodes. Nodes. Here is nodes. Here is from here to here is lambda by 2. Length. Total length is L here. Like this. And plus from here to here is lambda by 2. Plus from node, distance between node and antinode is lambda by 4. So finally we can calculate that is L is equals to 2 lambda by 2 plus here is lambda by 4. Finally, what is its length? The length is, here is the length is, L is equal to, so there is 4 lambda plus next one lambda. So finally it is 5 lambda by 4. Here is third wavelength of these waves. L is equals to 5 lambda 3 by 4. We need to calculate third wavelength. So that is lambda 3 is equals to 4L by 5. Now we know that that is what is V is equals to under root of T by mu. V, velocity of wave, V is equals to under root of T by mu. And the velocity of sound, V is equals to, here is N3 lambda 3. Now what is V? Here is substituting T by mu, that is equals to N3 into lambda 3. What is lambda 3? Lambda 3 is nothing but here is a 4L by 5. But we have to calculate N3. N3 is equals to, here is 5 by 4L and a root T by mu. So finally we should take common 5, 1 by 4L root T by mu. We know that 1 by 4L under root T by mu, that is fundamental frequency. I am writing here 5N, finally this is N3. So what is the ratio of these frequencies? So ratio of frequencies. Okay, N1 is to N2 is to N3. That is equals to, here is N is to N is to. And the second one is, what is scale? That is 3N is to 5N. Finally, 1 is to 3 is to 5. This is the frequency. Okay, ratio of frequency 1 is to 3 is to 5. Write it. And we are going to discuss about the standing waves on a string fixed at 2 ends. Fixed at 2 ends. Okay, string fixed at 2 ends. 2 ends means like this, 2 rigid supports we are taking here, like this. 1, 2, 3. Here is. We should take only first of all, first node, like this. Okay, now it's here is node, here is node, here is anti-node. Distance between two successive nodes is, we know that is lambda by 2. The length of this here is 2 ends, no? 2 rigid supports. Its length is taken L is equals to lambda by 2, but lambda 1 is considered here. Here, how many modes are formed here? P is equals to 1. Number of modes is only 1, means the first harmonic here. So that is L is equals to lambda 1 by 2. We need to calculate lambda 1. Lambda 1 is equals to, here is 2L. We know that the speed of wave V is equals to under root of T by mu. The wave velocity V is equals to N1 lambda 1 here, and so we can substitute here root T by mu, that is equals to N1 into, what is lambda 1? Lambda 1 is 2L. Now we need to calculate N1 is equals to N equal to, here is 1 by 2L and the root of T by mu. This is the fundamental frequency for the first mode, after formation of the first mode between 2 and. Next one is, here between 2 ends, number of modes are 2. So its length is L, like this. And nodes, here is anti-nodes, here is anti-nodes. Now 2 supports here. Length L is equals to, here is lambda by 2, lambda by 2. That is 2 lambda by 2. 2 lambda 2 by 2. We consider lambda 2 here. So we need to calculate lambda 2 here. 2L is equals to 2 lambda 2, but lambda 2 is equals to 2L by 2. So same as follows. Here is V is equals to, we know that under root T by mu, and the wave velocity here is written V is equals to under root of T by mu, and velocity of sound V is equals to N2 lambda 2. Here is V is under root of T by mu, that is equals to N2 into, what is lambda 2? Lambda 2 is 2L by 2. Finally, N2 is equals to, here is written 2 by 2L under root of T by mu. So that is, we should take common T 1 by 2L root T by mu. So it can be written as, here is, so N2 is equals to, okay, N2 is equals to, here 2 of 1 by 2L root T by mu. 1 by 2L and the root T by mu is, that is N, that is 2L. Now write it. Next, third harmonic is formed between the 2 ends. Third harmonic. Third harmonic means like this here. 1, 2. Here is like this. Third harmonic is formed between the two ends, and the wave is traveling like this, and it is coming to backward direction. After superimpositions, the waves are formed here, and its length is L from here to here. This is antinode, this is antinode, and this is also antinode. Here is nodes, nodes, node, and nodes are formed. And lambda by 2, here is the lambda by 2, here is lambda by 2. So lambda by 2, lambda by 2, lambda by 2. 3 lambda by 2. Here is, okay, that is L is equals to 3 lambda, 3 by 2. We can write like this. Distance between two successive nodes is lambda by 2. Here is plus lambda by 2. Here is plus lambda by 2. Totally, the length of these three modes between the two ends is taken as 3 lambda 3 by 2. Now, we need to calculate lambda 3. But lambda 3 is equals to here 2L by 3. We know that V is equals to under root of T by mu. And next one is velocity of sound. V is equals to N3. Here is lambda 3. Now we have to calculate after substituting these values. What is V? Here is V is T by mu. That is equals to N3 into what is lambda 3? 2L by 3. Now we need to calculate N3. N3 is equals to here is 3 by 2L and a root T by mu. So we should take common 3. Here is 1 by 2L. 1 by 2L and a root T by mu. So finally we can write it 3N. This is N3. This is N3. So we can write the ratio of frequency. Here is N1 is, N2 is, N3. That is equal to. So N1 is here N. N2 is, what is N2 is came 2N is. N3 is 3N. So finally the ratio is 1 is to 2 is to 3. Okay, this is standing waves on a string fixed at two ends. The ratio of frequencies 1 is to 2 is to 3. Okay, let me go to discuss about sonometer. Sonometer. Like this. It is one of the hollow wooden box. Okay, this is hollow wooden box. Wooden box. Now these are two bridges. These are bridges. Sharp bridges, and this is experimental wire. Experimental wire. Experimental wire. Now these are the weights. Here is weights. And this is pulley. Okay, it's a very simple experiment. This is one of the sonometer. Here is a sonometer is one of the operators. It is a hollow wooden box, and take a one string. It is one end of the string is attached to the small support, and it is passing through the sharp edges of the bridges, and it is over on the pulley, and the second end of the string is attached some weights. Here the weights are attached to the second end of the string. So, and it is getting a certain tension in the string after attaching the weights. So it's very simple, and so the two bridges are kept on the surface of the hollow wooden box. So like it is one of the operators, it is used to study the loss of stretched strings. Study the loss of stretched strings, or verify the loss of stretched strings. We know that. And to calculate the fundamental frequency after vibrating of the strings. It's very simple. And take one of the tuning fork, get it vibrates by a rubber hammer. The vibrating tuning forks keep near to the string at the time of two bridges are moving in opposite direction. So the vibration of influence is acts on the string, hence the string is also getting vibrations at the time of the paper rider is falls down. Then we have to calculate the length of the string between the two bridges. Okay, now due to that is called as a resonance, because of the how much frequency vibrating the tuning forks. Okay, the string is also vibrating with the same frequency, that is called as a resonance. Due to that resonance, it is getting vibrations, but do not touch the string by vibrating tuning fork to that of string. And so due to that resonance, the paper rider is falls down. This is paper rider. Paper rider. This is paper rider. When it falls down, then it can be stopped. Two bridges are stopped. Then we have to calculate the length of the string between the two bridges from here to here. We have to calculate the length when producing the maximum sound, when they are moving, okay, opposite in direction. At the time of the paper rider is falls down, okay, we can stop the two bridges. Then we have to calculate the length of the two bridges. Like that also. Here is, and we have to calculate the vibrations of the stretched string, that is the fundamental frequency of the string, and is equals to here 1 by 2L under root T by mu. Where T is a tension in the string, mu is a linear density, and L is the length between the two bridges. It is one of the very simple experiment to find out the maximum sound, to find out the length between two bridges, to verify the loss of stretched string, to study the loss of stretched strings. That purpose we have to use this experiment. Now here is the fundamental frequency of the that string, n is equals to 1 by 2L under root of T by mu. Here is n is equals to 1 by 2L root here T by mu is nothing but that is a linear density. Since here is mu is equals to rho A. So I can write it a rho A. Rho is density of the string, A is area of the string. That is equals to, here is 1 by 2L. We can write like this also, T by rho into pi r square. Area of the wire. Here is taken the area of the wire is rho pi r square. This is the frequency. So the frequency can be written as like this also, n is equals to 1 by 2L under root of T by rho pi r square. Also we can write it as. Now here, this is about the information of sonometer. And so what purpose of this? So it is used to study the loss of stretched string and observed maximum sound, okay, in this experiment. So what are the loss of stretched strings? What are the loss of stretched strings? Here the loss of stretched strings. Loss of stretched strings. Stretched string. So the first one is the fundamental frequency is inversely proportional to L. So here it's a very simple, it can be written as NL is equal to constant. So when it is possible, when the fundamental frequency of the stretched string which is inversely proportional to length, when L and T are constant. When L and T are constant, then the fundamental frequency is inversely proportional to length of the string. So we can write like this also. And here is this relation can be written as N1 by N2 equal to, here is L2 by N1. This is the first law of stretched string. And the second one is N is directly proportional to root T. When here is L and mu are constant. Mu are constant. See, it's very simple. Mu are constant string. When length and linear density are constants, here is N by, we can write like this, N by root T is equal to constant. So this relation can be written as like this also. Here is N1 by N2 is equals to root T1 by T2. This is second law of stretched string. Next we go to discuss about third one. Third laws of stretched string. That is N is inversely proportional to root M. Root M means here mu, linear density. Okay, when which are constant? L and T are constant. We can write like this also. The fundamental frequency is inversely proportional to square root of linear density. So we can write like this: N by N root M. N root M is equals to, here is constant, and we can write like this also: N1 by N2 equal to root mu2 by mu1, like this. So the fundamental frequency is inversely proportional to square root of linear density when L and T are constant, length of the string and the tension in the string is constant. It is possible. N1 by N2 equal to under root of mu2 by mu1. Next, the fourth one is here. N is inversely proportional to root rho. Density. The fundamental frequency is inversely proportional to square root of density of the string. So we can write like this: N root rho is equal to, here is constant. And when it is possible, when L, T and R are constants, like this. Here is, we can write like this. It can be written as N1 by N2 equal to, here is under root rho2 by rho1. This is the fourth law of stretched strings. The fundamental frequency is inversely proportional to square root of density of the string. We have written like this also. So when it is possible, when T, L and R are constants, radius is constants, So we have written like this, n1 by n2 equal to under root of rho 2 by rho 1. Thank you very much.